Good day everyone. My name is Marijoy Pakapak from BSED Science 2, and today I'm going to discuss to you the AC in a capacitor and AC in an inductor. So, let's take the first one, which is the AC in a capacitor. AC in a capacitor. Capacitor circuit characteristics. Expressed mathematically, the relationship between the current through the capacitor and the rate of voltage change across the capacitor is as such: I is equal to C dE all over dt. So this is the capacitor and rate of voltage formula. The expression dE or dt is one from calculus, meaning the rate of change of instantaneous voltage over time in volts per second. The capacitance C is in farads, and the instantaneous current I, of course, is in amps. Sometimes you will find the rate of instantaneous voltage change over time expressed as dV over dt instead of dE over dt, using the lowercase letter v instead or letter e to represent voltage, but it means the exact same thing. So to show what happened with alternating current, let's analyze a simple capacitor circuit. Pure capacitive circuit, capacitor voltage lags capacitor current by 90 degrees. So if we were to plot the current and the voltage for this very simple circuit, it would look something like this. Pure capacitive circuit waveform. So remember, the current through a capacitor is a reaction against the change in voltage across it. Therefore, the instantaneous current is zero whenever the instantaneous voltage is at a peak. Zero change or level slope on the voltage sine wave. And the instantaneous current is at a peak whenever the instantaneous voltage is at maximum change, the points of steepest slope on the voltage wave where it crosses the zero line. This results in a voltage wave that is negative 90 degrees, out of phase with the current wave. So looking at the graph, the current wave seems to have a head start on the voltage wave. The current leads the voltage, and the voltage lags behind the current. So as you might have guessed, the same unusual power wave that we saw with a simple inductor circuit is present in a simple capacitor circuit too. In a pure capacitive circuit, the instantaneous power may be positive or negative. As with the simple inductor circuit, the 90-degree phase shift between voltage and current result in a power wave that is alternate equally between positive and negative. So this means that a capacitor does not dissipate power as it reacts against change in voltage. It merely absorbs and releases power alternately. So now let's move on to a capacitor's reactance. A capacitor's opposition to change in voltage translates to an opposition to alternating voltage in general, which is by definition always changing in instantaneous magnitude and direction. For any given magnitude of AC voltage at a given frequency, a capacitor of given size will conduct a certain magnitude of AC current. Just as the current through a resistor is a function of the voltage across the resistor and the resistance offered by the resistor, the AC current through a capacitor is a function of the AC voltage across it and the reactance offered by the resistor. As with inductors, the reactance of a capacitor is expressed in ohms and symbolized by the letter X or Xc to be more specific. Since capacitor conduct current in proportion to the rate of voltage change, they will pass more current for faster changing voltage as they charge and discharge to the same voltage peak in less time and less current for slower changing voltage. What this means is that reactance in ohms for any capacitor is inversely proportional to the frequency of the alternating current. So this is the capacitor's reactance formula. Xc is equal to 1 over 2 pi Fc. So this is the reactance of 100 UF capacitor. So please note that the relationship of capacitive reactance to frequency is exactly opposite from that of inductive reactance. So capacitive reactance in ohms decreases with increasing AC frequency. Conversely, inductive reactance in ohms increases with increasing AC frequency. Inductors oppose faster changing current by producing greater voltage drops. Capacitor oppose faster changing voltage drops by allowing greater current. So as with inductors, the reactance equations 2 pi f term may be replaced by the lowercase Greek letter omega, which is referred to as the angular velocity of the AC circuit. Thus, the equation Xc is equal to 1 over 2 pi f C could also be written as Xc is equal to 1 over omega C, with omega cast in units of radians per second. Alternating current in a simple capacitive circuit is equal to the voltage in volts divided by the capacitive reactance in ohms, just as either alternating or direct current in a simple resistive circuit is equal to the voltage in volts divided by the resistance in ohms. So the following circuit illustrates this mathematical relationship by example. However, we need to keep in mind that voltage and current are not in phase here. So as was shown earlier, the current has a phase shift of positive 90 degrees with respect to the voltage. So if we represent these phase angles of voltage and current mathematically, we can calculate the phase angle of the capacitor's reactive opposition to current. Mathematically, we can say that the phase angle of a capacitor's opposition to current is negative 90 degrees, meaning that a capacitor's opposition to current is a negative imaginary quantity. So see the figure given. So this phase angle of reactive opposition to current becomes critically important in circuit analysis, especially for complex AC circuits where reactance and resistance interact. So now, let's move on to AC in an inductor. Expressed mathematically, the relationship between the voltage drop across the inductor and rate of current change through the inductor is as such: E is equal to L di over dt. Alternating current in a simple inductive circuit. The expression di over dt is one from calculus, meaning the rate of change of instantaneous current I over time in amps per second. The inductance L is in henries, and the instantaneous voltage E, of course, is in volts. So sometimes, you will find the rate of instantaneous voltage expressed as V instead of E. So V is equal to L di over dt, but it means the exact same thing. So to show what happens with alternating current, let's analyze a simple inductor circuit. Pure inductive circuit, inductor current lags inductor voltage. And if we were to plot the current and voltage for this very simple circuit, it would look something like this. Pure inductive circuit waveforms. Remember, the voltage drop across an inductor is a reaction against the change in current through it. Therefore, the instantaneous voltage is 0 whenever the instantaneous current is at the peak, zero change or level slope on the current sine wave. And the instantaneous voltage is at the peak whenever the instantaneous current is at maximum change, the points of steepest slope on the current wave where it crosses the zero line. So this results in a voltage wave that is 90 degrees out of phase with the current wave. So looking at the graph, the voltage wave seems to have a head start on the current wave. the voltage leads the current and the current lags behind the voltage. Things get even more interesting when you plot the power for this circuit. In a pure inductive circuit, instantaneous power may be positive or negative because instantaneous power is a product of the instantaneous voltage and the instantaneous current P is equal to IE. The power equals 0 whenever the instantaneous current or voltage is 0. Whenever the instantaneous current and voltage are both positive above the line, the power is positive. So as with the resistor example, the power is also positive when the instantaneous current and voltage are both negative below the line. However, because the current and voltage waves are 90 degrees out of phase, there are times when one is positive while other is negative, resulting in equally frequent occurrences of negative instantaneous power. But what does negative power mean? It means that the inductor is releasing power back to the circuit, while a positive power means that it is absorbing power from the circuit. Since the positive and negative power cycles are equal in magnitude and direction over time, the inductor releases just as much power back to the circuit as it absorbed over the span of a complete cycle. So what this means is that the reactance of an inductor dissipates net energy of quite unlike the resistance of a resistor, which dissipates energy in the form of heat. Mind you, this is for perfect inductors only, which have no wires resistance. So now let's move on to reactance versus resistance. An inductor's opposition to change in current translates to an opposition to alternating current in general, which is by definition always changing in instantaneous magnitude and direction. So this opposition to alternating current is similar to the resistance but different in that it always results in phase shift between current and voltage, and it dissipates zero power. Because of its differences, it has a different name, reactance. Reactance to AC is expressed in ohms, just like resistance is, except that its mathematical symbol is X instead of R. To be specific, reactance associated with an inductor is usually symbolized by the capital letter X with letter L as a subscript like this, XL. So this is the exact formula for determining reactance. XL is equal to 2 pi FL, reactance of a 10 mH inductor. In the reactance equation, the term 2 pi F, everything on the right hand side except the L, has a special meaning unto itself. It is the number of radians per second that the alternating current is rotating at. If you imagine one cycle of AC to represent a full circle's rotation. So if this constant 2 pi is multiplied by frequency in hertz cycle per seconds, the results will be figured in radians per seconds, known as the angular velocity of the AC system. Angular velocity in AC systems. Angular velocity may be represented by the expression 2 pi f, or it may be represented by its own symbol, the lowercase Greek letter omega, which appears similar to our Roman lowercase w. Thus, the reactance formula XL is equal to 2 pi FL could also be written as XL is equal to omega L. It must be understood that this angular velocity is an expression of how rapidly the AC waveforms are cycling, a full cycle being equal to 2 pi radians. It is not necessarily representative of the actual. It must be understood that this angular velocity is an expression of how rapidly the AC waveforms are cycling, a full cycle being equal to 2 pi radians. It is not necessarily representative of the actual shaft speed of the alternator producing the AC. Anyway, we express the angular velocity of the system. It is apparent that it is directly proportional to reactance in an inductor. So as the frequency or alternator shaft speed is increased in an AC system, an inductor will offer greater opposition to the passage of current and vice versa. Alternating current in a simple inductive circuit is equal to the voltage in volts divided by the inductive reactance in ohms, just as either alternating or direct current in a simple resistive circuit is equal to the voltage in volts divided by the resistance in ohms. An example circuit is shown here. Inductive reactance of 10 mH, inductor at 60 Hz. Anyway, we express the angular velocity of the system. It is apparent that it is directly proportional to reactance in an inductor. Phase angle. The voltage has a phase shift of positive 90 degrees with respect to the current. If we represent these phase angles of voltage and current mathematically in the form of complex numbers, we find that an inductor's opposition to current has a phase angle too. And for an inductor, current lags voltage by 90 degrees in an inductor. So mathematically, we say that the phase angles of an inductor's opposition to current is 90 degrees, meaning that an inductor's opposition to current is positive imaginary quantity. This phase angle of reactive opposition to current becomes critically important in circuit analysis, especially for complex AC circuits where reactance and resistance interact.